The sun looks calm from 93 million miles away, a flawless sphere of light, steady enough to feel eternal. But beneath that golden surface, magnetic fields twist, collide, and store unimaginable energy. One violent release could send radiation racing toward Earth at the speed of light, followed by billions of tons of magnetized plasma. The sky might glow with beautiful auroras while satellites fail, radio signals disappear, and power grids struggle under currents generated from space. Could a solar storm truly bring modern civilization to a standstill, or are the darkest warnings overstated? Thank you for spending part of your day or night here. Please share what time it is where you are listening and which city or country you're joining from in the comments. And if calm journeys through science help make the universe feel a little closer, leave a like, subscribe, and share this video with someone who enjoys the mysteries hidden behind familiar things. Now, let the quiet surface of the sun fall away and enter the restless magnetic world beneath it. The sun seems almost perfectly calm from a distance, a pale sphere suspended in darkness, smooth at the edge and steady in its light. Its daily presence encourages the idea of permanence. It rises, crosses the sky, and sets with such regularity that it appears less like a violent star and more like a silent clock. Yet that appearance is misleading. Beneath the visible surface, the sun is never still. Matter rises, falls, twists, and circulates through layers of crushing pressure and enormous heat. Magnetic fields coil through that moving material, gathering energy in forms that remain invisible until they suddenly break. Most of the time, this activity passes without consequence for life on Earth. At other times, the same star that warms oceans and sustains forests releases bursts of radiation and vast clouds of charged plasma into space. These events are known collectively as solar storms, and their effects can stretch across the entire solar system. The question is not whether the sun is dangerous in the ordinary sense. Its light is already powerful enough to shape climate, weather, and the chemistry of life. The deeper question is whether a rare and extreme eruption could strike modern civilization at its most vulnerable points, not by burning cities from the sky, but by disturbing the invisible systems that hold the technological world together. The sun is not a solid object. Its outer regions consist of plasma, a state of matter formed when heat becomes intense enough to separate electrons from atomic nuclei. In ordinary gas, atoms remain mostly intact. In plasma, charged particles move more freely, and their motion creates electric currents. Those currents generate magnetic fields, while magnetic fields guide the movement of the charged particles in return. The result is a continuous exchange between matter and magnetism, each shaping the other, deep inside the sun. Energy produced by nuclear fusion moves outward over immense spans of time. Closer to the surface, hot plasma rises, cools slightly, and sinks again in broad convective patterns. The sun also rotates, but not as a rigid body. Regions near the equator turn more quickly than regions closer to the poles. This uneven rotation stretches and winds the magnetic field, gradually making it more complex. What begins as a broad global pattern can become tangled into loops, arcs, and concentrated knots. These magnetic structures often emerge through the visible surface as dark sunspots, which appear cooler than their surroundings but remain intensely hot by any earthly standard. Sunspots are signs that powerful magnetic fields are interfering with the normal flow of heat. They often gather in active regions where eruptions become more likely. The solar surface therefore does not simply glow, it carries a changing map of hidden stress. Above it lies the corona, the sun's outer atmosphere, a vast and faint region that extends far beyond the visible disk. The corona is much hotter than the surface below, a fact that remains one of the enduring puzzles of solar physics. It also releases a constant stream of particles called the solar wind. This wind moves outward in every direction, carrying the sun's magnetic influence through interplanetary space. Earth travels within that flow at all times. Under ordinary conditions, the solar wind passes around the planet's magnetic field and produces only gentle disturbances. The magnetosphere, the region dominated by Earth's magnetism, acts like a broad shield. It is compressed on the side facing the sun and drawn into a long tail on the night side. This shield is not a solid wall. It bends, vibrates, and changes shape as conditions in the solar wind shift. Even during quiet periods, charged particles enter near the polar regions and collide with gases high in the atmosphere. Those collisions create auroras, curtains of light that reveal the meeting of solar particles and Earth's magnetic defenses. The beauty of an aurora hides the scale of the forces involved. A calm display may result from only a modest disturbance, while a severe storm can push auroras far from the poles and alter the behavior of the upper atmosphere across the planet. Solar activity rises and falls in a cycle lasting roughly 11 years. Near solar minimum, fewer sunspots appear and major eruptions become less common. Near solar maximum, the magnetic field grows more disordered, active regions multiply, and the chance of powerful events increases. The cycle is regular in broad outline but unpredictable in detail. A quiet day can still produce a strong eruption, and an active region can rotate into view with magnetic structures already close to instability. The sun therefore combines rhythm with uncertainty. Its long patterns can be tracked, but the exact timing and strength of individual storms remain difficult to forecast. The first major form of eruption is a solar flare. A flare is a sudden release of electromagnetic radiation from an active region, often caused by magnetic reconnection. During reconnection, magnetic field lines arranged in a stressed configuration break and join in a new pattern. The field rapidly loses stored energy, heating plasma and accelerating particles. The released radiation can include visible light, ultraviolet energy, and X-rays. Because this radiation travels at the speed of light, it reaches Earth in about 8 minutes. There is no long warning once the flare begins. The same flash that announces the event is already arriving. Strong X-ray and ultraviolet emissions can alter the ionosphere, a charged layer of Earth's upper atmosphere used by some radio signals. This can cause radio blackouts, especially on the sunlit side of the planet. High-energy particles may follow, moving more slowly than light but still arriving quickly. These solar energetic particles can be dangerous to spacecraft electronics and to astronauts beyond the protection of Earth's lower atmosphere. They can also affect aircraft travelling near the poles, where Earth's magnetic field offers less shielding and where certain communication routes depend on high-frequency radio. Yet a solar flare alone is not usually the greatest threat to power grids. The more serious danger often comes from a coronal mass ejection, commonly called a CME. A CME is an immense eruption of magnetized plasma from the corona. It can contain millions or billions of tons of material and can expand as it travels, forming a huge cloud that moves through the solar wind. Some CMEs travel relatively slowly and take several days to reach Earth. Others move at extraordinary speed and cross the distance in less than a day. Not every CME is directed toward Earth. Many pass harmlessly above, below, or beside the planet. Even a direct impact does not guarantee disaster. The outcome depends on speed, density, magnetic structure, and especially the orientation of the CME's magnetic field. Earth's field points in different directions across space, and the arriving cloud carries its own field. When the two fields are poorly aligned, The magnetosphere may resist much of the disturbance when they align in the wrong way. However, magnetic reconnection can occur on the sunward side of Earth. Energy then enters the magnetosphere more efficiently. The protective shield does not vanish, but it becomes disturbed and loaded with energy. The night side stretches farther into space, storing magnetic tension in its long tail. Eventually, part of that energy can snap back toward Earth, driving currents through the upper atmosphere and intensifying the geomagnetic storm. At ground level, the event may remain almost silent. No wall of fire crosses continents. No blast wave moves through streets. The danger appears instead as changing magnetic fields spread across vast regions. According to the principles of electromagnetism, a changing magnetic field can induce an electric current in a conductor. Modern civilization is filled with long conductors. Power lines extend across countries. Pipelines cross wide landscapes. Undersea cables connect continents. Rail networks, communication systems, and electrical infrastructure form linked pathways through which induced currents can move. The longer the conductor and the larger the magnetic disturbance, the greater the possible effect. In this way, a storm beginning in the solar atmosphere can reach down into transformers and transmission lines on Earth. The sun does not need to touch the ground. It only needs to disturb the magnetic environment surrounding the planet. This is the quiet contradiction at the heart of solar weather. Human bodies are largely protected by the atmosphere and magnetic field, yet the machine supporting modern life can remain exposed. The sun appears calm because its violence is distant. Civilization appears secure because its most fragile systems are usually invisible. Between them lies a narrow layer of space where magnetic fields meet, bend, and sometimes open a path for energy to enter. Most days, the shield holds with a little consequence. On rare days, the same connection that paints the polar sky can begin to test the electrical foundations of the world. The sun is often described as a ball of gas, but that familiar phrase hides the state of matter that truly defines it. Gas suggests atoms drifting freely while remaining mostly intact. The sun is hotter and more restless than that. In its outer layers, atoms are stripped apart, electrons separate from atomic nuclei, and the material becomes plasma, a sea of charged particles whose behavior is governed not only by heat and pressure, but also by electricity and magnetism. This distinction matters because neutral gas can move without creating powerful electrical effects, while plasma cannot move without carrying charge. Every rising current, every sinking stream, and every twisting flow inside the sun becomes part of an electrical system on a scale far beyond anything found on Earth. The sun therefore does not merely contain magnetic fields, it continuously creates, stretches, compresses, and rearranges them. Plasma is common throughout the universe. Stars are made of it. The solar wind is made of it, and much of the thin matter between stars exists in plasma form. On Earth, plasma is less familiar because the surface environment is cool enough for atoms to remain whole. It appears in lightning, auroras, certain flames, and artificial devices, but these are brief or limited examples. Inside the sun, plasma is the normal state of matter. The temperature near the visible surface reaches several thousand degrees, while deeper regions become vastly hotter. Under those conditions, collisions are so energetic that electrons cannot remain bound to nuclei. The resulting particles move in enormous numbers, each responding to electric and magnetic forces. Their motion forms currents, and those currents build magnetic fields that extend across the solar atmosphere and far into space. To understand why solar storms occur, it is necessary to understand this relationship between moving charge and magnetism. A charged particle travelling through a magnetic field does not simply continue in a straight line. The field bends its path, often forcing it into a spiral around invisible magnetic lines. At the same time, streams of charged particles generate their own magnetic influence. The plasma shapes the field, and the field shapes the plasma. Neither can be treated as a passive background. They move together in a coupled system, sometimes smoothly and sometimes with growing tension. This coupling gives the Sun its structure. Bright arcs of plasma rise above the surface because the material follows curved magnetic loops. Dark sunspots appear where strong magnetic fields suppress the normal upward flow of heat. Long filaments stretch across the solar disk, held in place by magnetic forces even as gravity pulls them downward. The visible patterns are therefore traces of an invisible architecture. Beneath the surface, the plasma is constantly in motion. Heat rising from deeper layers drives convection, the same broad process that causes warm material to rise and cooler material to sink in a pot of heated water. On the Sun, however, convection occurs across distances larger than continents. The surface is covered with countless bright cells, each representing hot plasma rising in the center and cooler plasma descending around the edges. These cells exist for only a short time before being replaced by new patterns. Beneath them lie larger and slower flows that help transport energy outward. The entire surface seems to boil, not with liquid water, but with luminous charged matter moving under pressure, gravity, and magnetic force. The Sun also rotates, and this rotation adds another layer of complexity. Because the Sun is not solid, different latitudes rotate at different speeds. The equatorial regions complete a turn more quickly than the regions near the poles. Over time, this uneven rotation drags magnetic field lines around the star. A field that begins with a relatively simple shape becomes wound around the Sun, stretched eastward and folded through moving plasma. Convection disturbs it further, pushing parts of the field upward while pulling others downward. What was once broad and orderly becomes crowded with loops, knots, and regions of opposing magnetic direction. This changing pattern is known as the solar dynamo, the process through which the motion of conducting plasma sustains the Sun's magnetic field. The dynamo is not a single machine hidden inside the star. It is the combined effect of rotation, convection, electrical currents, and magnetic feedback operating throughout the solar interior. The word suggests steady production, but the solar dynamo also produces cycles of instability. Roughly every 11 years, the number of sunspots rises and falls. At the beginning of a cycle, spots tend to appear at middle latitudes. As the years pass, they emerge closer to the equator, near the peak. Active regions become more common and eruptions occur more frequently. Near the end, activity declines, and the global magnetic field reverses direction. The north magnetic pole becomes south, and the south becomes north. Another cycle then begins. This periodic reversal reveals that the solar magnetic field is not fixed. It is rebuilt again and again by the moving plasma beneath the surface. Yet the cycle does not behave like a perfect clock. Some peaks are strong, others weak. Some active regions release repeated eruptions, while others remain quiet despite complex magnetic structure. The general rhythm is known, but the precise behavior of the field remains difficult to predict. This uncertainty comes partly from the scale of the system. The Sun contains layers moving at different speeds and depths. Magnetic fields can emerge, reconnect, sink, or spread across the surface. Small changes in one region can influence larger structures. The plasma is turbulent, meaning its motion contains swirls within swirls, from broad circulation patterns to smaller chaotic flows. Turbulence makes long-range prediction difficult because tiny differences can grow over time. Solar physicists can observe active regions and measure their magnetic complexity, but the exact moment when stored energy will be released often remains uncertain. The same active region may produce a weak flare, a powerful flare, a coronal mass ejection, or no major eruption at all. Magnetic fields carry energy because they resist being bent and twisted. A simple field can be imagined as a stretched elastic line, though the reality is more complex. When plasma motions drag the field into a distorted shape, energy accumulates. The field may remain stable for hours or days, holding plasma in suspended arches above the surface. A prominence can rise as a vast loop, glowing along the edge of the sun or appearing dark against the brighter disk. Some remain quiet and slowly change. Others become unstable, lifting away as the surrounding magnetic structure breaks apart. The plasma follows the changing balance of magnetic pressure, gravity, and surrounding forces. Once that balance fails, motion can accelerate rapidly. The sun's appearance of solidity also contributes to misunderstanding. The visible surface, called the photosphere, looks like a sharp boundary, but it is only the layer from which most visible light escapes. There is no ground beneath it. Looking downward means entering denser and hotter plasma, not reaching a solid crust. Above it lies the chromosphere, a thinner layer where jets and waves rise through the magnetic network. Beyond that lies the corona, an atmosphere so extended that it gradually blends into the solar wind. Each layer has different temperatures, densities, and magnetic conditions, yet all are connected. A disturbance that begins below the photosphere can shape an active region above it. A magnetic loop in the corona can store energy built by motions deep within the star. An eruption from that loop can then travel across interplanetary space and reach Earth. The path from the solar interior to human technology is therefore not a direct blast from a simple surface. It is a chain of connected processes beginning with moving plasma and ending with changing magnetic fields around another world. The more closely the sun is observed, the less smooth it becomes. High-resolution images reveal granules, dark spots, bright points, arcing loops, rising filaments, and sudden flashes. Instruments that detect ultraviolet and X-ray radiation show structures invisible to human eyes. Magnetograms map the direction and strength of fields across the surface, exposing regions where opposite polarities press close together. These boundaries often become sites of instability because the magnetic field is forced into complicated arrangements. Observatories in space watch continuously, tracking the growth and decay of active regions as the sun rotates. Their measurements do not remove uncertainty, but they reveal the conditions from which eruptions emerge. Beneath every flare and every coronal mass ejection lies the same underlying fact: the sun is made of electrically charged matter in motion. Its light may appear steady, but its magnetic body is constantly being rebuilt. Plasma rises, currents flow, field lines twist, and energy gathers in places too distant to hear and too bright to watch directly. The calm disk in the sky is not a quiet object. It is the visible face of an electrical ocean, moving without rest, carrying within its currents the power to shape the space around every planet. Deep beneath the sun's visible surface, there is no single wheel, engine, or hidden core turning magnetism on and off. The solar magnetic dynamo is a distributed process, spread through vast layers of moving plasma and sustained by the star's rotation, heat flow, and electrical conductivity. It is less like a machine with separate parts and more like a restless pattern that continuously rebuilds itself. Hot material rises from deeper regions. Cooler material sinks, and broad currents carry charged particles through the solar interior. Because those particles carry electric charge, their movement creates electrical currents. Those currents generate magnetic fields, and the magnetic fields then influence the next movement of the plasma. The process feeds back into itself, producing order without stillness and structure without permanence. At the largest scale, the Sun possesses a global magnetic field with broad north and south polar regions. Yet this global field is only the simplest outline. Beneath and above it lies a crowded landscape of smaller loops, twisted bundles, and concentrated patches of magnetic force. Some fields remain buried for a time, pushed downward by surrounding flows. Others become buoyant and rise through the plasma, eventually breaking through the photosphere. When they emerge, they often form pairs of sunspots with opposite magnetic polarity, marking the two ends of a loop that continues beneath the surface. These regions reveal how the dynamo reaches upward from the solar interior and leaves visible traces on the star's face. The Sun's rotation is central to this process because it does not rotate uniformly. The equator turns faster than the higher latitudes, while deeper layers can move at different speeds from those above them. This differential rotation stretches the magnetic field in the direction of rotation. A field that begins with a broad connection from one pole to the other becomes wrapped around the Sun over time, as though a loose thread were being wound around a spinning sphere. The comparison is incomplete because magnetic fields are not physical chords, but it captures the way rotation stores complexity. The more the field is stretched, the more strongly it becomes concentrated in bands beneath the surface. These bands can remain hidden until convection and magnetic buoyancy lift parts of them upward. The place where the pattern changes most sharply is thought to be a thin region near the base of the convection zone, where the Sun's outer turbulent layers meet a deeper interior that rotates more evenly. This boundary is called the tachocline. It is not directly visible, but observations of waves moving through the Sun allow scientists to infer how the interior rotates. In the tachocline, differences in speed may shear magnetic fields and strengthen them before they rise. The solar dynamo is not confined to this boundary, and many details remain uncertain, but the tachocline appears to play an important role in organizing the large-scale magnetic cycle. Above it, convection carries the field through layers where motion becomes increasingly turbulent. Turbulence introduces both creativity and unpredictability. Rising and sinking plasma does not follow a single smooth path. It breaks into cells, vortices, and shifting streams. Each motion can twist a magnetic structure slightly, move one part of it faster than another, or bring regions of opposite polarity closer together. Across the surface, these countless small actions gradually alter the global field. At the same time, large circulation patterns move magnetic flux toward the poles and along the surface. The result is a dynamo shaped by processes acting across many scales, from broad flows extending across the star to smaller motions that change from hour to hour. The familiar solar cycle emerges from this complicated system. During solar minimum, the global field is relatively simple, and sunspots are few. As differential rotation wins the field, magnetic bands strengthen and active regions begin to appear. Sunspot numbers rise, eruptions become more common, and the solar atmosphere grows increasingly disturbed. Near solar maximum, the field reaches its most tangled state. The polar regions weaken, the old global pattern begins to break down, and new magnetic polarity starts to take its place. Eventually, the Sun's north and south magnetic poles reverse. The reversal does not occur all at once or with perfect symmetry. One pole may change before the other, and the field can remain disordered for a time. Afterward, activity declines, a simpler global pattern returns, and the next cycle begins with opposite polarity. The The full magnetic pattern therefore takes about 2 ordinary sunspot cycles to return to its original orientation. This longer rhythm reveals that the sun does not merely grow active and quiet, it repeatedly overturns its magnetic identity. Yet even this broad cycle varies. Some cycles produce many sunspots and strong eruptions, while others remain weak. The timing shifts, the peaks differ in height, and individual active regions behave in ways that resist simple prediction. The dynamo remembers parts of its past because magnetic fields from one cycle influence the next, but the memory is incomplete. Small differences in plasma flow can change how much magnetic flux reaches the poles, how strongly new bands form, and where active regions emerge. This makes long-range forecasting difficult. Scientists can estimate the general rise and fall of activity, but they cannot predict every future sunspot or eruption. The uncertainty is not a sign that the dynamo is random. It is a sign that many interacting processes create a system whose broad behavior is organized while its details remain sensitive to change. Sunspots are among the clearest surface signs of this hidden engine. They appear dark because strong magnetic fields reduce the upward transport of heat, making the region cooler than the surrounding photosphere. They are not cold, only less bright. A single, large sunspot can exceed Earth in size, while complex groups can spread across enormous regions. Their magnetic structure matters more than their appearance. Simple groups with clearly separated polarities may remain stable. More complicated groups, especially those where opposite polarities press together in narrow boundaries, can store much greater energy. These regions often produce strong flares because their fields have been twisted and stressed by motion below the surface. The dynamo creates the field, but local plasma flows determine how tightly that field becomes wound before it releases energy. The connection between deep motion and surface eruption is still being studied. Instruments can map magnetic fields at the photosphere, yet the three-dimensional structure above and below remains harder to measure. Scientists reconstruct likely field shapes using observations and physical models, but hidden layers introduce uncertainty. Waves traveling through the solar interior provide clues, much as seismic waves reveal the structure beneath Earth's crust. This field of study, called helioseismology, measures subtle motions on the solar surface and uses them to infer deeper flows. It reveals bands of faster and slower rotation, changes near the tachocline, and patterns that migrate as the cycle progresses. These measurements show that the sun's magnetic activity is connected to movements far beneath the regions where eruptions become visible. The dynamo also shapes the solar wind. Magnetic fields rising through the corona can form closed loops that trap plasma, or open structures that allow particles to escape more freely into space. Dark regions in ultraviolet images, known as coronal holes, often contain open magnetic fields and produce faster streams of solar wind. As the sun rotates, these streams sweep through the solar system and can disturb Earth's magnetosphere even without a major eruption. Near solar maximum, the global magnetic structure becomes more complex, and the boundary between open and closed fields changes constantly. The entire heliosphere, the vast region filled by the solar wind, responds to the evolving dynamo at its center. Every planet moves within that changing magnetic environment. The dynamo therefore links the sun's deepest accessible layers to events far beyond the star itself. It governs the rise and fall of sunspots, guides the architecture of the corona, changes the solar wind, and prepares the magnetic structures that later release flares and coronal mass ejections. It does not choose when a storm will strike Earth, and it does not aim eruptions toward any world. It simply sustains a cycle of creation, distortion, reversal, and renewal. For most of human history, this engine works unseen. marked only by rare auroras or dark spots glimpsed through protected instruments. Modern observatories reveal more of its motion, but not all of its rules. Beneath the calm disk, charged matter continues to circulate, carrying old magnetic patterns downward and lifting new ones toward the surface. The sun's field is never finished. It is being made, unmade, and made again. And every solar storm begins somewhere within that slow, immense act of magnetic renewal. Magnetic fields can remain stretched and twisted for long periods without releasing their energy, yet they do not remain stable forever. Across the solar surface, plasma continues to move beneath and around them, pulling their footpoints apart, pushing regions of opposite polarity together, and forcing already complex structures into even tighter arrangements. The field resists this distortion. Energy accumulates in the corona, stored not as heat alone, but in the shape and tension of the magnetic structure itself. From a distance, an active region may appear almost unchanged, marked only by dark sunspots and bright loops. Within it, however, the field may be approaching a threshold where the old arrangement can no longer hold. The transition from stability to eruption often begins through magnetic reconnection, a process in which field lines break their previous connections and join in a new pattern. The word break is only a useful description, because magnetic fields are not ropes or wires. They represent the direction and strength of magnetic force through space. Yet in a highly conducting plasma, matter tends to move along these field lines, making the invisible structure behave as though it were woven into the plasma. When different parts of the field are pressed together in opposing directions, thin regions of intense electrical current can form. Within those narrow layers, the plasma conditions change enough for the old magnetic arrangement to collapse and a new one to emerge. Reconnection releases energy with astonishing speed. Magnetic tension that has built for hours or days can suddenly accelerate particles, heat plasma, and launch waves through the solar atmosphere. The result may be a solar flare, a coronal mass ejection, or both. A flare is primarily a burst of electromagnetic radiation. A coronal mass ejection is a vast eruption of magnetized plasma. They often occur together because both can arise from the same unstable magnetic region, but neither guarantees the other. A powerful flare may occur without a large ejection, while a major ejection may rise with only a modest flash. Their relationship depends on how the magnetic field is arranged, and whether the surrounding corona allows the erupting structure to escape. In some active regions, strong overlying fields act like a cage. Energy is released, particles are heated, and radiation brightens. But most of the plasma remains confined near the sun. In others, the upmagnetic structure opens or weakens, allowing a rising mass to push outward into space. Before such an eruption, a long filament may rest above the surface, supported by twisted magnetic fields. Seen against the bright solar disk, it appears dark because it is cooler and denser than the material behind it. Seen along the edge of the sun, the same structure may glow as a prominence, arching high into the corona. Some filaments remain stable for many days, others slowly rise as though the magnetic support beneath them is loosening. The ascent may begin almost imperceptibly, then accelerate when the surrounding field can no longer restrain it. As the filament rises, it stretches the field below into a long, narrow current sheet. Reconnection begins beneath the escaping structure, cutting and rejoining magnetic connections. Newly closed loops form below, while the upper structure is released farther outward. This process can feed additional energy into the eruption, allowing it to grow rather than fade. The flare brightens beneath the rising mass, and the coronal mass ejection expands above it. The event is not a simple explosion from a single point. It is a rapid reorganization of a magnetic system that may span distances larger than Earth. One possible path toward eruption is called the kink instability, a magnetic flux rope, a twisted bundle of field and plasma, can become so tightly wound that it begins to coil around itself. The structure loses its previous balance and rises or writhes through the corona. Another path is called the torus instability, which occurs when the restraining field above a rising flux rope weakens too quickly with height. The upward magnetic force then exceeds the downward confinement, and the structure escapes. These terms describe different aspects of instability, and real eruptions may involve more than one process. The exact trigger can be difficult to identify, because observations reveal the solar atmosphere from the outside, while the decisive changes unfold within a three-dimensional magnetic field. Models reconstruct the likely structure, but no instrument directly traces every field line through the corona. What appears sudden may be the final step of a slow transformation that has been building beneath the visible surface. Active regions emerge carrying magnetic complexity from below. Surface flows then shear the field along boundaries between opposite polarities. Small magnetic patches move, merge, and cancel. New flux may rise into an older field, disturbing its balance. Each change can bring the system closer to instability without revealing the exact moment when release will occur. This is why an active region can look threatening for days and remain quiet, while another produces a major flare with limited warning. Scientists measure sunspot structure, magnetic gradients, electrical currents, and changes in ultraviolet and X-ray emission. Yet the final threshold remains difficult to forecast precisely. The field does not announce how much additional stress it can hold. Once reconnection begins, energy moves through several channels. Part of it heats plasma to temperatures far above those of the visible surface. Part accelerates electrons and protons to very high speeds. These particles travel along magnetic field lines and collide with denser material lower in the solar atmosphere, producing intense radiation. Some energy drives shock waves and large-scale disturbances across the corona. Some contributes to lifting and accelerating the coronal mass ejection. The proportions differ from one event to another. A flare may release energy across a broad range of wavelengths, from radio waves to X-rays. The strongest radiation reaches Earth at the speed of light, revealing that the eruption has already occurred. The particles and plasma follow later, their arrival times depending on speed and the paths opened by the magnetic field. The violence of reconnection does not require the magnetic field to disappear. Instead, the field settles into a lower energy configuration. After a major eruption, bright arcades of loops often appear above the active region, tracing newly reconnected magnetic lines filled with hot plasma. These loops can remain visible as they cool. Above them, the ejected structure continues outward, expanding into the solar wind. The region may still contain enough stress for further eruptions, and active regions sometimes produce several flares and ejections in sequence. When multiple coronal mass ejections travel along similar paths, a later and faster one can catch an earlier, slower cloud. Their interaction can compress magnetic fields, increase particle acceleration, and create a more complicated disturbance in interplanetary space. A storm reaching Earth may therefore carry the history of several eruptions rather than one isolated event. The direction of an ejection also matters. Solar eruptions spread outward from the Sun in 3 dimensions, but observations from Earth flatten that geometry into a bright disk. A coronal mass ejection directed toward Earth may appear as a halo expanding around the Sun in coronagraph images, because the cloud is moving broadly along the line of sight. An eruption near the edge of the visible disk is easier to see from the side. Yet it may miss Earth entirely. Spacecraft positioned at different points can provide additional views and help reconstruct the true speed and direction. Even then, the internal magnetic orientation of the cloud may remain uncertain until it passes instruments closer to Earth. This hidden orientation can determine whether the magnetosphere experiences only a moderate disturbance or a severe geomagnetic storm. The danger is therefore shaped long before the cloud arrives, inside the magnetic geometry of the eruption itself. Most reconnection events never threaten civilization. Small flares occur often, and many coronal mass ejections travel into empty space. Even large eruptions may be directed away from Earth or carry magnetic fields that interact weakly with the planet. Yet the process that releases them is capable of converting stored magnetic energy into radiation and motion on an immense scale. The Sun does not need to become globally unstable. A limited active region can hold enough energy to alter conditions across millions of kilometers of space. For days, the warning signs may remain confined to subtle changes in sunspots and coronal loops. Then the magnetic structure rearranges, and the quiet appearance breaks. Light flashes outward first. Particles begin to race along open fields. Behind them, a cloud of plasma expands through the corona, carrying its own magnetic field into the solar system. The event begins as a change in invisible connections above the solar surface, but its consequences depend on where those new connections lead. Solar eruptions do not all leave the Sun in the same form, and the differences between them determine how quickly they arrive, what they disturb, and how much warning Earth receives. A solar flare is a burst of radiation. A solar energetic particle event is a storm of fast-moving charged particles, often dominated by protons. A coronal mass ejection is a vast cloud of plasma carrying an embedded magnetic field. These events can occur together, but they are not interchangeable. One active region may release a flare without launching a major cloud. Another may send a coronal mass ejection outward with only a modest flash. In the most powerful cases, all three develop in sequence, beginning with light, followed by particles, and ending with a much larger magnetic structure that reaches Earth hours or days later. The first signal is often the flare. When magnetic reconnection rapidly releases stored energy, the solar atmosphere brightens across many wavelengths. Visible light may increase, but the most important effects often come from ultraviolet radiation and X-rays. These forms of energy travel through space at the speed of light, crossing the distance between the Sun and Earth in about 8 minutes. By the time instruments detect the flare, its radiation is already interacting with the upper atmosphere. There's no opportunity to stop it, and little opportunity to prepare for that first arrival. The radiation does not normally penetrate to the surface in dangerous amounts because the atmosphere absorbs it high above the ground. Its strongest immediate effects occur in the ionosphere, where solar energy changes the number and behavior of charged particles. Radio waves passing through this region can be weakened, bent, or absorbed. High-frequency communication may fade across the sunlit side of Earth, affecting aircraft, ships, emergency services, and remote regions that depend on long-distance radio links. Navigation signals can also be disturbed when the ionosphere becomes uneven, introducing errors into the timing and path of signals from satellites. The flare is therefore not a wave of fire sweeping over the planet. It is a sudden change in the electrical conditions of the upper atmosphere. Some flares also accelerate particles to extreme speeds. Electrons and protons can be driven outward along magnetic field lines, forming a solar energetic particle event. These particles travel more slowly than light, but far faster than the ordinary solar wind. The earliest can arrive near Earth in less than an hour, especially when the magnetic connection between the erupting region and the planet provides a direct path. Their motion is not simply radial. They spiral around the magnetic field carried by the solar wind, following a curved route through interplanetary space. This means an eruption that is not aimed directly at Earth can still send particles toward the planet if the magnetic field lines connect the two regions. Proton storms matter most beyond the protection of the lower atmosphere. Satellites can experience electrical charging, damaged components, false signals, and memory errors when energetic particles strike sensitive electronics. Solar panels may lose efficiency over time. Detectors can become flooded with noise, making scientific measurements difficult or temporarily impossible. Astronauts face a more direct hazard because energetic particles can pass through spacecraft walls and deposit energy in living tissue. Missions beyond low Earth orbit are especially exposed, since the shielding provided by the planet's magnetic field becomes weaker with distance. A strong particle storm during travel to the Moon or Mars could require crews to shelter in the most protected part of a spacecraft, surrounded by water, supplies, or other dense material. Aircraft flying near the poles also receive greater exposure because magnetic field lines guide particles toward high latitudes. Airlines may alter routes during severe events, reducing both radiation risk and communication problems. The largest and slowest arrival is the coronal mass ejection. A CME is not merely a dense gust of the solar wind. It is an expanding structure of plasma and magnetic field torn from the corona. At launch, it may already span a region larger than Earth, and as it moves outward it grows wider, sometimes reaching a scale that covers a large part of the space between planets. The material inside can include electrons, protons, and heavier ions. But its danger comes as much from the magnetic field it carries as from the particles themselves. This internal field survives the journey through space and determines how strongly the cloud couples with Earth's magnetosphere. CMEs vary greatly in speed. A slow one may move at only a few hundred kilometers each second and take several days to arrive. A fast one can travel at well over 1,000 kilometers each second and cross the distance in less than a day. Speed changes more than arrival time. A fast CME can drive a shockwave through the solar wind, compressing plasma and magnetic fields ahead of it. That shock can accelerate additional particles and produce a sudden disturbance when it reaches Earth. The magnetosphere may be compressed on the sunward side. Satellites in high orbits may briefly find themselves in a harsher environment, and electrical currents in near-Earth space can intensify. The storm then deepens if the magnetic field inside the CME is oriented in a direction that favors reconnection with Earth's field. The three parts of a major solar event therefore follow different clocks. Radiation arrives first, announcing that energy has been released. Energetic particles may follow within tens of minutes or several hours, bringing danger to spacecraft and high-altitude systems. The CME arrives later, carrying the possibility of a geomagnetic storm that can last for many hours or even days. This sequence provides both a challenge and an opportunity. The earliest effects occur almost immediately, but the slower plasma cloud can sometimes be tracked while it is still traveling through space. Solar observatories watch the corona with instruments that block the bright disk and reveal faint material moving outward. By comparing images over time, scientists estimate the cloud's speed, width, and direction. Spacecraft positioned away from Earth provide additional angles, helping distinguish a cloud moving toward the planet from one passing to the side. Even with these observations, forecasts remain uncertain because the cloud expands, interacts with the solar wind, and can change speed during the journey. Its internal magnetic orientation is even harder to determine from afar. A CME may appear large and direct, yet produce only a moderate storm if its magnetic field connects poorly with Earth's. Another may seem less dramatic but carry a long interval of strongly opposing field, allowing energy to enter the magnetosphere efficiently. This hidden structure is one of the most important uncertainties in space weather prediction. Instruments near Earth can measure the field directly before the cloud arrives, but their position provides only a limited warning, often less than an hour before the most important magnetic conditions reach the planet. By then, operators may already be preparing satellites and power systems, yet the final severity of the storm only becomes clear as the cloud passes those monitors. Solar eruptions can also interact with one another. A fast CME launched after a slower one may catch it in space. The later cloud can compress the earlier cloud, strengthen magnetic fields, and create a more complex disturbance. Repeated eruptions from the same active region may clear a path through the solar wind, allowing a later CME to travel with less resistance and arrive faster than expected. Particle storms may continue between eruptions, raising the background radiation level before the largest cloud arrives. These compound events are difficult to model because the space between Sun and Earth is no longer a simple environment. It carries the remains of earlier activity, each disturbance changing the conditions faced by the next. The most serious solar storms are therefore not defined by a single flash or cloud. They are chains of connected processes. A flare alters the upper atmosphere almost immediately. Energetic particles threaten machines and people beyond strong shielding. A CME reshapes the magnetosphere and drives currents through near-Earth space. Each stage acts on a different part of civilization. From radio communication and navigation to satellites, aviation, and electrical grids, most events remain limited. Many flares are weak, many particle storms are modest, and most CMEs miss Earth or interact gently with its magnetic field. Yet the Sun occasionally aligns speed, direction, particle energy, and magnetic orientation in a single event. When that happens, the danger grows not because one phenomenon becomes magical or unknown, but because several familiar processes arrive together, each opening the way for the next. Earth is not exposed to the full force of the Sun without protection. The planet is surrounded by layers of defense formed by its atmosphere, magnetic field, and distance from the solar surface. These defenses do not block every disturbance, and they do not make space weather harmless, but they absorb, redirect, and weaken much of the energy that arrives. Without them, solar radiation and charged particles would reach the lower atmosphere far more easily, and conditions at the surface would be very different. The first shield is distance. The Sun is immensely powerful, yet Earth orbits far enough away for its energy to spread across a vast sphere before reaching the planet. Even so, sunlight remains strong enough to warm the surface and drive weather. While ultraviolet and X-ray emissions can alter the upper atmosphere, the next shield is the atmosphere itself, a deep layer of gas dense enough below to absorb most harmful radiation. X-rays and the most energetic ultraviolet light are stopped high above the ground. They transfer their energy to atoms and molecules in the upper atmosphere, ionizing them and changing their electrical state. This protects the surface, but it also creates the ionosphere, a region where solar activity can disturb radio communication and navigation. The same layer that absorbs dangerous radiation can therefore become a pathway through which solar storms affect technology. Most people at ground level remain physically safe during even a strong flare because the atmosphere blocks the direct radiation. The danger shifts upward, towards satellites, spacecraft, high-altitude aviation, and systems that depend on signals passing through the ionosphere. Earth's magnetic field provides another form of protection. It is generated mainly by motion in the planet's liquid outer core, where electrically conducting iron circulates and sustains a planetary dynamo. The field extends far into space, forming the magnetosphere. On the side facing the Sun, Pressure from the solar wind compresses this magnetic region. On the night side, the field is drawn into a long tail that reaches far beyond Earth. The shape changes continuously because the solar wind is never perfectly steady. Faster streams press against slower ones, magnetic directions shift, and waves move through the surrounding plasma. The magnetosphere responds by bending, vibrating, and transferring energy through its boundaries. It is not a rigid shield, but a flexible one. Charged particles approaching Earth are guided by magnetic forces. Many are deflected around the planet rather than allowed to enter directly. Others become trapped in radiation belts, regions where energetic particles spiral along magnetic field lines and bounce between northern and southern latitudes. These belts help prevent some particles from reaching the atmosphere, but they also create a hazardous environment for satellites. Protection is therefore never absolute. The magnetic field moves danger away from the surface while concentrating some of it in particular regions of near-Earth space. Near the poles, the geometry of the field allows particles to travel deeper into the upper atmosphere. Magnetic field lines curve downward there, guiding electrons and ions toward the air below. When these particles collide with oxygen and nitrogen, they transfer energy to the atoms and molecules. The excited gases then release that energy as light. Oxygen can produce green and red emissions, while nitrogen contributes blue, violet, and crimson tones. The result is the aurora, one of the most visible signs that solar material has entered Earth's magnetic environment. During quiet conditions, auroras remain near the polar regions. During stronger geomagnetic storms, the disturbed magnetic field allows auroral activity to spread toward lower latitudes. The aurora is beautiful, but it is not merely decoration. It reveals that electrical currents are flowing through the upper atmosphere and that energy from the solar wind is being deposited into the planet's magnetic system. Those currents form part of a larger network connecting the magnetosphere and ionosphere. When solar conditions intensify, the network strengthens. Currents flow along magnetic field lines into and out of the upper atmosphere, while broad horizontal currents cross the polar regions. Their changing magnetic effects can reach the ground. The same process that creates light overhead can therefore affect equipment far below. Under most conditions, Earth handles this energy without severe consequences. The magnetosphere stores part of it, redirects part, and releases part through auroral activity and disturbances in the tail. A major coronal mass ejection changes the balance. When its shock arrives, the magnetosphere may be compressed suddenly. The boundary on the day side moves inward, and satellites in high orbits can be exposed to conditions normally found outside the shield. The pressure increase produces a rapid magnetic disturbance, often marking the beginning of a geomagnetic storm. The most important phase follows when the magnetic field carried by the CME points in a direction that favors reconnection with Earth's field. In that configuration, magnetic energy passes more efficiently through the dayside boundary. Field lines join with the solar wind, are pulled over the poles, and stretch into the magnetotail. Energy accumulates in the tail until reconnection occurs there as well, sending particles and magnetic flux back toward Earth. This process can trigger substorms, sudden intensifications of auroral activity that release stored energy over the polar regions. The upper atmosphere heats and expands. Its density increases at altitudes where many satellites orbit, producing additional drag. Spacecraft can lose altitude more quickly than expected, and operators may need to adjust their orbits. Satellites also encounter stronger radiation, charging, and disturbances in navigation signals. The atmosphere protects the ground by absorbing energy, but that absorption changes the atmosphere itself. The ionosphere becomes more irregular, the thermosphere swells, and currents strengthen across high latitudes. Each response reduces or redistributes part of the incoming energy while creating new challenges for technology. Earth's defenses also vary with location. High-latitude regions are more directly connected to the magnetosphere, so power grids and communication systems there often face greater geomagnetic exposure. Ground conductivity matters as well. Electric currents induced in the Earth follow paths shaped by local geology. Regions with resistive rock may produce stronger voltage differences across the surface, increasing currents in long transmission lines. Coastlines can create additional complexity because land and seawater conduct electricity differently. This means the same solar storm can affect one region more severely than another, even when both lie at similar latitude. The strength of Earth's magnetic field also changes slowly over time. Magnetic poles drift, and the field has reversed many times in the planet's history. These reversals unfold over long periods rather than occurring as sudden collapses. During such transitions, the field can become more complicated and may weaken in some regions, but the atmosphere remains an important barrier against radiation. Modern civilization has never experienced a full magnetic reversal, so the exact technological consequences remain uncertain. Yet ordinary variations already show that protection is not identical everywhere. One region over the South Atlantic has a weaker magnetic field, allowing trapped particles to approach closer to Earth. Satellites passing through this area often take precautions because electronics can experience higher radiation exposure. The existence of this weak region does not mean the planetary field is failing. It shows that the shield has structure, with stronger and weaker zones shaped by processes deep inside Earth. Solar storms test that structure from the outside. The atmosphere and magnetosphere protect life so effectively that the direct human danger at the surface is usually limited. A severe storm does not strip away the atmosphere, boil oceans, or expose the ground to the full radiation of the sun. The more realistic threat lies in the systems placed beyond or within the edges of those defenses. Satellites operate where radiation is stronger. Radio signals cross regions altered by solar energy. Power networks stretch across the ground beneath changing magnetic fields. The shield keeps flesh and bones safe while leaving metal, silicon, and long electrical conductors vulnerable in different ways. This contrast explains why auroras can brighten without immediate physical harm to people below, even as operators monitor satellites and power grids with increasing concern. Earth's natural defenses are powerful, but they were not formed to protect a technological civilization. They reduce a stellar eruption from a direct environmental catastrophe to a complex electrical disturbance. That reduction is extraordinary, yet it does not remove the danger. It changes its form. Solar energy is absorbed in the upper atmosphere, redirected along magnetic field lines, stored in the magnetotail, and released through currents and auroras. By the time the disturbance reaches the surface, it is no longer a cloud of plasma crashing into the ground. It has become a pattern of changing magnetism spread across a planet, quiet enough to remain unseen and broad enough to enter the infrastructure on which modern life depends. A geomagnetic storm begins long before its effects reach the ground. It begins inside a cloud of solar plasma moving through interplanetary space, carrying a magnetic field that formed near the Sun and survived the journey outward. By the time the cloud approaches Earth, it may be wider than the planet's orbit around the Moon. Yet its most important feature is not its size. The decisive factor is the direction of the field embedded within it. Earth's own magnetic field points northward on the sunward side of the planet. When the arriving solar field also points mainly northward, the two systems resist strong connection, and much of the disturbance flows around the magnetosphere. When the solar field points southward, the geometry changes. Opposing magnetic directions meet across the dayside boundary, and reconnection allows energy from the solar wind to enter Earth's magnetic environment far more efficiently. The magnetosphere remains present, but its outer layers begin to open, stretch, and rearrange under pressure. The first contact often comes as a shock. A fast coronal mass ejection plows through the slower solar wind ahead of it, compressing plasma and magnetic fields into a moving front. When this front reaches Earth, the magnetopause, the outer boundary of the magnetosphere, is pushed inward. Ground instruments may record a sudden jump in magnetic strength, while satellites encounter a rapid change in particle density and pressure. This initial compression can last only a short time, but it announces that a much larger structure is following. Behind the shock lies a disturbed sheath of plasma, turbulent and irregular, followed by the main magnetic cloud. The sheath can already drive strong activity if its field turns southward for long enough. The cloud itself may then deepen the storm as its internal field rotates and maintains a favourable orientation for reconnection. The severity of the event depends not only on how strongly the field points southward, but also on how long that condition persists. A brief interval may produce a modest disturbance. Several hours of strong southward field can load the magnetosphere with far greater energy. Reconnection on the day side changes the shape of Earth's field. Magnetic lines exposed to the solar wind are dragged over the polar regions and pulled behind the planet. The night side stretches into an increasingly long magnetotail, with two broad lobes of oppositely directed magnetic field separated by a thin current sheet. Energy accumulates there as the solar wind continues to pull. The tail becomes a reservoir of magnetic tension, storing the work done by the incoming storm. This process is gradual compared with the flare that began the event, yet it can transform the entire near-Earth environment. The magnetosphere grows more distorted, the polar regions become more active, and charged particles gain access to paths that are normally less open. Eventually, the tail can no longer store energy at the same rate. Reconnection begins within the current sheet, severing some of the stretched field and creating new closed lines that snap back toward Earth. The motion is not a simple elastic recoil, but the effect is similar. Magnetic tension accelerates plasma earthward, and bursts of particles enter the inner magnetosphere. Some are guided along field lines into the upper atmosphere, where they intensify the aurora. Others circle the planet, contributing to a large electrical current known as the ring current. This current flows through populations of energetic ions and electrons trapped around Earth. As it strengthens, it produces a magnetic field that partly opposes the planet's own field at the surface. Ground-based measurements therefore show a broad weakening during the main phase of a geomagnetic storm. The deeper the depression, the more intense the storm is considered to be. The ring current does not form instantly. It grows as particles are injected and energized over several hours, while repeated disturbances in the tail add new material. The storm may unfold through a series of substorms, each releasing part of the stored energy. Auroral arcs brighten, break apart, and spread across the sky. Currents flowing along magnetic field lines connect the magnetosphere to the ionosphere, while horizontal currents strengthen across the polar regions. These current systems are not confined to space. Their magnetic fields extend downward and change across the surface of Earth. Rapid changes are especially important because they can induce voltages in long conductors. The same geomagnetic storm that glows silently above the poles can therefore create electrical effects in power lines thousands of kilometers away. The storm also heats the upper atmosphere. Energetic particles collide with gases, and stronger currents dissipate energy through electrical resistance. The thermosphere expands as it warms, increasing the density of the thin air at satellite altitudes. Low-orbit spacecraft encounter greater drag and may lose altitude. Their predicted paths can become less accurate, complicating collision avoidance and tracking. Navigation signals passing through the ionosphere may be delayed or scattered as the charged layers become irregular. Radio communication can fade in some regions and become noisy in others. These effects arise from the same transfer of solar energy, but they develop differently across altitude, latitude, and local time. A geomagnetic storm is therefore not a single impact. It is a planet-wide sequence of coupled responses. The dayside field reconnects, the tail stores energy, the nightside releases it. Particles enter the inner magnetosphere, currents intensify, and the atmosphere changes. Each part influences the next. The orientation of the solar field remains central throughout the process. A fast cloud with weak or northward magnetism may compress the magnetosphere without producing a severe storm. A slower cloud with a prolonged southward field can transfer more energy and drive stronger consequences. This explains why the apparent size or brightness of a solar eruption does not always predict the disturbance at Earth. The most important magnetic component is difficult to measure from the Sun because the internal structure of a coronal mass ejection evolves as it travels. Scientists estimate its likely orientation from the active region that produced it, from the shape of solar filaments, and from models of the expanding field. These clues improve forecasts but do not remove uncertainty. Direct measurement usually comes from spacecraft positioned upstream of Earth, where the solar wind arrives before reaching the magnetosphere. Such monitors can detect the shock, plasma density, speed, and magnetic direction, offering a final warning that the most geo-effective part of the cloud is approaching. That warning may be less than an hour. During the storm, the magnetosphere can become compressed enough to expose satellites in high orbits to harsher plasma conditions. Charged particles collect on spacecraft surfaces, sometimes building unequal electrical potentials that discharge through sensitive systems. Energetic particles penetrate electronics and produce false commands or damaged memory. At the same time, the expanding upper atmosphere increases drag on lower satellites. The disturbance reaches several orbital regions at once, but in different forms. A spacecraft near geostationary orbit may face charging and radiation, while one in low orbit faces drag and changing atmospheric density. Systems on the ground experience induced currents shaped by the speed of magnetic change and the electrical properties beneath them. The recovery phase begins only after energy input declines. The solar field turns northward, the cloud passes, or the solar wind pressure weakens. Reconnection on the dayside slows, and the magnetotail is no longer loaded as strongly. The ring current gradually loses particles through collisions, charge exchange, and escape. Magnetic measurements move back toward normal. The upper atmosphere cools and contracts, though satellite orbits may continue to reflect the disturbance. Auroras retreat toward higher latitudes. Recovery can take many hours or several days, and new solar activity can interrupt it before the system fully settles. Multiple eruptions arriving close together may prevent the magnetosphere from returning to quiet conditions, creating a prolonged and complicated event. None of this means that Earth's magnetic field has failed. A geomagnetic storm is the behavior of the shield under stress. It absorbs, redirects, stores, and releases energy rather than simply blocking it. That response protects the surface from direct contact with the solar plasma, but it also creates electrical currents and atmospheric changes that matter to technology. The shield becomes a pathway because magnetic reconnection joins the solar wind to Earth's field. Energy that would otherwise pass around the planet enters through that connection and spreads through a vast network of currents, particles, and waves. The storm is born not when the cloud first leaves the sun, and not when auroras appear, but when two magnetic systems meet in the right orientation and begin to exchange energy. From that moment, the space around Earth becomes part of the eruption, and the planet's own magnetic field carries the disturbance inward. A geomagnetic storm becomes a threat to civilization only when its changing magnetic fields find long paths through which electrical currents can flow. The storm does not pour electricity directly from the sky into cities. Instead, it changes the magnetic environment around Earth, and those changes create electric fields across the ground. Where the surface and subsurface conduct electricity, the fields drive slow currents through rock, soil, seawater, pipelines, railway systems, and power networks. These are known as geomagnetically induced currents. They are weak across a short distance, but modern infrastructure extends across hundreds or thousands of kilometers. A small voltage spread over a vast region can therefore become a significant current once it enters a long conductor. The danger is not that every wire suddenly becomes charged beyond control. It is that systems designed for alternating current begin to experience an unwanted direct current, quietly pushing components beyond the conditions for which they were built. High-voltage power grids are especially exposed because they depend on long transmission lines and large transformers. Transformers raise voltage for efficient transmission and lower it again for local distribution. Inside each transformer, coils of wire surround a magnetic core. Under normal operation, alternating current creates a magnetic field that rises and falls in a controlled rhythm. A geomagnetically induced current changes this balance. Because it behaves more like direct current, it can shift the transformer's operating point and push the core towards saturation. Once saturation begins, the transformer draws more reactive power, generates unwanted harmonics, heats unevenly, and becomes less efficient at controlling voltage. The process may begin without obvious external damage. A transformer can still appear intact while its internal temperature rises and its behavior becomes unstable. Across a connected grid, many transformers may experience the same disturbance at once. Reactive power demand increases. Voltage control becomes more difficult. Protective devices may respond to distorted signals, and operators may lose an accurate picture of what the network is doing. If voltage falls too far in one region, transmission lines can disconnect. Power then shifts onto neighboring paths, loading them more heavily. Another line trips, then another, and the disturbance can cascade. The original cause comes from space, but the blackout develops through the ordinary logic of an overloaded electrical network. Each protective action is intended to save equipment, yet many correct local actions can combine into a regional failure. The collapse of the Quebec power grid during a geomagnetic storm in the late 20th century demonstrates this chain. Rapid magnetic changes induced currents through the ground and into the transmission system. Protective equipment reacted. Key parts of the grid disconnected, and the network failed within a short period. Millions of people lost power even though the storm did not directly destroy power stations or transmission lines. The event shows how quickly a magnetospheric disturbance can become a terrestrial emergency when a large grid is carrying heavy loads. Geography also matters. Quebec lies at a relatively high magnetic latitude, where geomagnetic activity is often stronger. Its underlying geology includes resistive rock that can produce larger surface electric fields during magnetic disturbances. A similar storm does not affect every network equally, because grid design, latitude, ground conductivity, line direction, and transformer type all shape the current that enters. Pipelines provide another long path. Metal pipes extending across great distances can carry geomagnetically induced currents between regions with different electrical potential. Pipelines are protected against corrosion by systems that control the voltage between the metal and the surrounding soil. Solar storm currents can interfere with those conditions, making measurements unreliable and increasing corrosion risk if disturbances are strong or prolonged. The effect is usually not an immediate rupture. It is a quieter engineering problem in which severe magnetic activity complicates the long-term protection of buried infrastructure. Railway signalling systems can also be affected because tracks and cables form extended conductors. Disturbances may alter track circuit currents or produce false indications, requiring operators to slow traffic or use alternative procedures. Undersea communication cables are more complex. Modern fiber optic cables transmit information as light, which is not directly disrupted by geomagnetic currents in the same way as old telegraph wires. Yet the cables contain powered repeaters along the ocean floor. An electrical current is supplied through conductive elements running across great distances. Their design includes protection and grounding, but extreme geomagnetic conditions remain a concern because ocean and coastal conductivity can shape induced voltages over continental scales. The historical warning comes from the telegraph era. During the Great Storm of the 19th century, telegraph systems carried currents produced by the changing magnetic field. Operators reported sparks, electrical shocks, and equipment that continued to function after local batteries were disconnected. The network was simple compared with modern infrastructure, but its long wires made it an accidental detector of space weather. That event revealed the basic vulnerability before electrical grids, satellites, and digital communication became essential to daily life. Modern systems are better protected, yet they are also more numerous, interconnected, and deeply woven into every service. Satellites face a different electrical environment. They operate directly within charged plasma and radiation. During a storm, particles collect on spacecraft surfaces and within insulating materials. If one part of a satellite charges more strongly than another, an electrostatic discharge can occur. A tiny arc may damage a circuit, corrupt a command, or trigger a temporary failure. Energetic particles can penetrate electronic components and alter stored information, creating single-event upsets in computers. A bit changes state, a sensor produces a false reading, or a processor resets. Radiation can also degrade solar panels and detectors over time. Engineers designed spacecraft with shielding, fault detection, redundant systems, and recovery procedures. But no satellite is completely immune. A severe storm can affect many spacecraft at once, reducing the ability to rely on another satellite when one fails. Navigation systems are vulnerable through both space and atmosphere. Their satellites may experience charging radiation and orbit changes, while their signals pass through an ionosphere distorted by solar energy. A navigation receiver estimates position by measuring the travel time of signals from several satellites. Irregular electron density can delay those signals by different amounts, producing errors that grow during intense storms. Aviation, shipping, agriculture, surveying, financial timing, emergency response, and communication networks all depend on precise satellite timing and positioning. A disturbance measured in small timing errors can therefore spread into many sectors without appearing as a single dramatic failure. Radio communication faces similar complexity. A flare can cause immediate absorption of high-frequency signals on the sunlit side of Earth. Later, particle precipitation and geomagnetic activity can disrupt polar communication. The ionosphere may reflect signals more effectively or absorb and scatter them. Conditions change across regions and over time, making stable communication difficult. Aircraft crossing polar routes, ships far from shore, and communities beyond terrestrial networks may depend on these radio paths. A storm does not need to silence every channel to create risk. It only needs to interrupt the routes used when reliability matters most. The greatest concern comes from simultaneous disruption. A power grid problem becomes harder to manage when communication is unreliable. Satellite failures become more serious when navigation is degraded. Repair crews move more slowly when fuel distribution, traffic control, and digital coordination are interrupted. A single transformer failure is an engineering task. Many failures across several regions become a supply and logistics problem. Large high-voltage transformers are expensive, difficult to transport, and often built to specific network requirements. They are not stored everywhere in large numbers. Severe internal heating can damage insulation and shorten transformer life even when immediate failure does not occur. If enough large units are permanently damaged, restoration may take much longer than recovery from an ordinary blackout, yet the most catastrophic outcomes are not automatic. Grid operators monitor geomagnetic conditions, measure induced currents, adjust power flows, reduce stress on vulnerable equipment, and temporarily remove some components from service. Satellites can enter safer operating modes, postpone maneuvers, and limit sensitive activities. Airlines can reroute flights, and communication services can shift frequencies or methods. These actions turn forecasting into protection. The better the warning and the clearer the understanding of local vulnerability, the more effectively systems can reduce exposure before the strongest currents arrive. The danger from electricity generated by space weather is therefore neither imaginary nor inevitable. It emerges where natural magnetic change meets human scale. A field moving across the planet produces only a small electric force at any one point, but infrastructure gathers that force across distance. Long lines, large networks, and synchronized systems transform a broad disturbance into concentrated stress. Civilization becomes vulnerable, not because the sun sends a precise electrical weapon toward Earth, but because modern society has built conductive pathways across the landscape and orbital systems beyond the atmosphere. The storm supplies the changing magnetism. The network provides the route. Between them, invisible currents begin to move. Long before satellites, global power grids, and digital communication, solar storms were already reaching Earth with enough force to disturb technology. The machines of the 19th century were simple by modern standards, but they were connected by long wires stretched across great distances. That made them unexpectedly sensitive to changes in Earth's magnetic field. The most famous warning arrived in the late summer of 1859, when a large group of sunspots appeared on the Sun, and a brilliant flare was observed from Earth. The eruption that followed drove an intense geomagnetic storm now known as the Carrington Event. It remains one of the strongest solar disturbances documented in the era of direct human observation, and its effects revealed how quickly activity on the Sun could enter the systems of civilization. The first signs were visible in the sky. Auroras spread far beyond their usual polar regions, appearing across places where such light was rarely seen. Reports described red, green, and white glows reaching into lower latitudes, bright enough in some areas to illuminate the night. People woke believing dawn had arrived. Newspapers could be read under the unusual light. The display was beautiful, but it also marked a powerful transfer of energy into Earth's magnetic environment. Currents in the upper atmosphere intensified, magnetic instruments moved violently, and the same changing fields induced currents in telegraph networks below. Telegraphy was then one of the most advanced communication systems in the world. Messages travelled as electrical pulses through wires connecting cities, railways, ports, and governments. During the storm, these networks began to behave in ways operators had never intended. Sparks jumped from equipment. Paper caught fire in some offices. Operators received shocks, signals became erratic, and communication failed across wide regions, in several places. Telegraph systems continued to transmit even after their batteries were disconnected, powered for a time by currents induced through the storm itself. The sun had turned the network into part of a planetary electrical circuit. The event did not destroy civilization because civilization had not yet built its basic functions around electricity. Most homes had no electrical supply. Water systems, food distribution, navigation, medicine, and finance did not depend on digital networks or satellites. When telegraph lines failed, the disruption was serious, but the rest of society continued to operate through physical transport, local systems, and human labour. The Carrington Event therefore became a warning whose full meaning would only emerge later. It showed that a sufficiently strong solar storm could affect technology over continental distances. What it could not show was how such a storm would interact with a world covered in power lines, transformers, communication cables, satellites, and precise timing systems. More than a century later, another event provided a smaller but more modern lesson. In March of 1989, a strong geomagnetic storm struck Earth after solar eruptions sent disturbed plasma through interplanetary space. The storm intensified currents in the upper atmosphere and produced rapid magnetic changes across the ground. In Quebec, those changes entered the power network. Protective systems detected abnormal conditions and disconnected key parts of the grid. Within a short time, the network collapsed, leaving millions of people without electricity. The blackout lasted for hours, not years, and the system was eventually restored. Yet the speed of the failure was striking. A process beginning on the sun had crossed space, disturbed the magnetosphere, induced currents through the ground, and brought down a regional power grid with almost no visible damage in the streets. The Quebec blackout demonstrated that modern grids could fail, not because generators had run out of fuel or transmission, towers had fallen, but because magnetic conditions in space had altered the behavior of electrical equipment. It also revealed how local conditions shape the impact. Quebec's high magnetic latitude increased exposure to strong geomagnetic activity, while the underlying geology encouraged larger electric fields across the surface. The grid itself contained long transmission lines and equipment sensitive to unusual currents. The storm was global, but the consequences were concentrated where natural and technological vulnerability overlapped. Other regions experienced disturbances without suffering the same collapse. This difference matters because it shows that solar storm risk is not evenly distributed. A severe event can create a patchwork of effects, with some networks remaining stable while others face dangerous currents, voltage problems, or equipment stress. History contains other warnings as well. Strong geomagnetic storms have repeatedly disrupted radio communication, damaged satellites, altered spacecraft operations, and increased drag in low Earth orbit. During some events, navigation systems have become less reliable. Airlines have changed polar routes, and power operators have taken protective action. Many of these incidents remain limited because the storms were moderate, the vulnerable systems were prepared, or the magnetic orientation of the arriving plasma was less damaging than it might have been. Their importance lies in accumulation. Each event exposes another connection between solar activity and technological infrastructure. One storm affects communication, another disturbs a grid, another damages a spacecraft or shifts satellite orbits. Together, they reveal that space weather does not attack a single system. It tests many systems through different physical pathways, often at the same time. The Carrington Event remains central because it represents a scale that modern civilization has not yet experienced directly. Estimates of its strength contain uncertainty because scientific instruments were limited and measurements were not standardized in the way they are today. Researchers reconstruct the storm from magnetometer records, auroral reports, telegraph failures, and traces preserved in natural archives. The exact intensity is still debated, and it is possible that some later storms approached parts of its strength. Even so, the event stands as evidence that the Sun can produce disturbances far larger than the storms encountered during the modern satellite age. It is not a mythical upper limit, only a historical example. The solar system offers further reminders. In July of 2012, a powerful coronal mass ejection crossed Earth's orbit, but missed the planet because Earth was elsewhere along its path. Spacecraft measurements showed that the eruption was exceptionally strong and had been accelerated by earlier solar activity that altered the space ahead of it. Had Earth been in the direct path, the resulting geomagnetic storm could have placed severe stress on satellites and power grids. The near miss does not prove that global collapse would have followed, but it removes any comfort based on the idea that events of Carrington scale belong only to the distant past. The Sun remains capable of producing them. The difference between a historical disaster and an unnoticed passage can be only the position of Earth in its orbit when the cloud arrives. These warnings must also be interpreted with care. Solar storms are often described in extreme language, yet the historical record does not show civilization being returned to a primitive age. The Carrington Event damaged telegraph systems, but did not burn cities. The Quebec storm caused a major blackout but did not permanently destroy the regional grid. Modern satellites and power networks are vulnerable, but they are also monitored, protected, and operated by people who understand more about space weather than earlier generations did. The lesson of history is therefore not that collapse is certain, it is that effects can become serious quickly, and that rare events expose weaknesses that ordinary operation never reveals. Prepared systems can survive conditions that unprepared systems cannot. The greatest uncertainty comes from scale. A storm stronger than Quebec but weaker than Carrington might cause scattered failures, temporary communication problems, and controlled shutdowns. A direct Carrington-scale impact could create wider and longer disturbances, especially if transformers were damaged rather than merely disconnected. The outcome would depend on the state of the grid, the time of day, power demand, local geology, storm duration, and the magnetic orientation of the CME. History provides examples, but not a complete prediction. No past event perfectly reproduces the connected world of the present. That is why the old telegraph sparks remain important. They are a simple record of a larger principle. The Sun can induce electricity across a planet, and human networks can gather that energy into places never designed to receive it. The red auroras of 1859 and the darkened cities of Quebec belong to different technological eras, yet they describe the same chain of cause and effect. A magnetic field changes far above Earth. Currents appear below. Machines begin to behave strangely. Systems fail where their resilience is weakest. The warning is not hidden in speculation. It is already written in the history of wires, lights, and storms. Modern civilization is not held together by a single machine or network. It is held together by layers of dependence linked so closely that one failure can weaken many others. Electricity powers communication, water treatment, transport, refrigeration, hospitals, banking, fuel distribution, and the controls that keep factories and warehouses moving. Satellites provide navigation, weather monitoring, timing, and communication. Radio systems connect aircraft, ships, emergency services, and remote communities. During an ordinary blackout, many of these systems continue through backup power, local reserves, and nearby unaffected regions. A severe solar storm becomes more dangerous when several layers are disturbed at once, and recovery depends on the very systems that are also failing. The deeper problem develops through accumulation. A satellite enters safe mode, a navigation signal becomes unreliable, a transformer overheats, a transmission line disconnects to protect itself. None of these events alone ends modern life. Together, across wide regions and over many hours, they can create a crisis whose scale is difficult to judge from any single control room. Power is the central vulnerability because nearly every other modern service assumes that electricity is available, stable, and continuous. Large grids are designed to survive ordinary failures. Generators are spread across regions. Transmission paths provide alternatives, and protective devices isolate damaged equipment before it can pull the network down. Yet geomagnetically induced currents are unusual because they can enter many parts of a grid simultaneously. A storm does not need to break one important station. It can place stress across a broad area, pushing transformers towards saturation, increasing reactive power demand, distorting waveforms, and reducing the margin operators rely on during emergencies. As lines disconnect, power shifts onto remaining routes. The grid becomes less flexible at the same moment that accurate measurement may become harder. A cascading failure can then spread beyond the areas experiencing the strongest induced currents. In the mildest outcome, operators reduce loads, separate parts of the grid, and restore service after the storm passes. In a more severe outcome, some large transformers suffer permanent damage. These devices are massive, specialized machines built for specific network conditions. Replacing one may require long manufacturing schedules, heavy transport, custom installation, and careful testing. Most grids do not store many full replacements because of their cost and size. A handful of damaged units can be managed. Large numbers across several countries would create a repair problem shaped by manufacturing capacity, transportation limits, and competition for the same scarce equipment. Electricity also supports the production of replacement parts, making prolonged outages harder to solve than short ones. Water systems are among the first essential services to feel extended power loss. Pumps move water from rivers, reservoirs, and underground sources into treatment plants and through distribution networks. Treatment requires chemical processes, monitoring, and pressure. Wastewater systems depend on pumps as well. Backup generators can maintain critical operations for a time, but they need fuel, maintenance, and working supply routes. If grid power remains unstable and fuel deliveries slow, pressure falls and treatment quality becomes harder to guarantee. Authorities may issue restrictions or boil water notices, yet communication may also fail. A technological disturbance from space then becomes a public health problem on the ground. Not because solar particles reach drinking water, but because the machines protecting it lose power. Hospitals are built with emergency generation, but those systems are designed to bridge temporary outages, not necessarily a regional failure lasting weeks. Intensive care equipment, operating rooms, laboratories, sterilization units, refrigeration, ventilation, and digital records all depend on reliable electricity. Generators consume fuel and require servicing. Deliveries may compete with emergency vehicles, communication sites, water plants, and food distribution centers. Medical supply chains also depend on factories, warehouses, transport scheduling, and cold storage. A hospital can remain illuminated while becoming steadily less capable as oxygen, medicines, blood products, and sterile materials are used faster than they can be replaced. The crisis develops through depletion rather than sudden darkness. Food systems are similarly dependent on constant movement. Farms use electric pumps, refrigeration, automated feeding, processing equipment, and fuel distribution. Warehouses track inventory and maintain controlled temperatures. Trucks depend on working pumps at fuel depots and clear navigation across road networks. Supermarkets hold only a limited amount of stock for the populations they serve. Refrigerated goods begin to spoil when power is lost, while replacement deliveries slow if communication and fuel systems are disrupted. The fields may still produce food, and warehouses may still contain it, yet the chain between production and consumption weakens. Modern scarcity often begins not with an absolute lack of resources, but with a failure to move them. Fuel itself depends on electricity. Refineries require power and control systems. Pipelines use electrically operated pumps. Storage terminals rely on automated loading equipment. Retail stations cannot dispense fuel without electricity unless they have independent backup systems. Emergency generators may therefore face a circular problem. They need fuel to produce power, while the fuel network needs power to deliver fuel. Strategic reserves can reduce this risk, but distribution remains essential. A region with ample fuel in storage may still experience shortages if pumps, roads, communications, or payment systems are unavailable. Transport slows, repair crews travel less efficiently, and every other recovery effort becomes more difficult. Communication systems are more resilient than they appear in some ways and more fragile in others. Fiber optic networks carry vast amounts of data with little direct sensitivity to geomagnetic currents, but their routers, switching centers, cooling systems, and local access points need electricity. Mobile towers often have batteries or generators, yet those reserves are limited. Satellite communication may provide alternatives, although satellites themselves can be affected by radiation and charging. Emergency networks can prioritize essential traffic, but severe regional disruption creates enormous demand exactly when capacity is reduced. Digital communication may continue unevenly, with some areas connected and others isolated. The result is not total silence but fragmented awareness. Authorities may know that several systems are failing without knowing conditions in every community. Financial systems depend on both electricity and time. Electronic payments, bank records, trading platforms, automated clearing, and cash machines rely on data centers and secure communication. Many also depend on satellite timing signals. Backup clocks and terrestrial networks provide resilience, but widespread timing disruption would require careful management. During prolonged outage, shops may be unable to process electronic payments even when goods remain available. Cash becomes more useful, yet the supply of physical currency is limited, and distribution requires functioning transport and security. Economic activity slows because trust and verification become harder. Businesses cannot coordinate deliveries, wages, contracts, or inventories normally, deepening the interruption to supply chains. Navigation failures create another layer of difficulty. Aircraft and ships use several independent systems, and professional crews do not rely on a single satellite signal. Even so, modern transport networks are optimized around precise positioning. Ports schedule vessel movements, cranes, containers, and trucks through digital coordination. Aircraft routes, rail operations, road freight, surveying, agriculture, and emergency response become less efficient when positioning errors grow. A severe storm may force delays, route changes, and wider safety margins. The world does not stop moving, but it moves more slowly and with less certainty. That loss of efficiency matters during recovery, when every spare transformer, generator, fuel shipment, and repair team must reach the right location quickly. The most frightening descriptions of solar catastrophe often leap directly from grid failure to the end of civilization. The real danger is more gradual and conditional. Local failures can be contained when neighbouring regions provide power, equipment, fuel, and personnel. National failures can be managed when international supply chains remain available. The threat becomes civilizational only when the disturbance is broad enough, the damage deep enough, and the response fragmented enough that normal support systems cannot compensate. Even then, societies retain knowledge, tools, institutions, and the capacity to organize. A solar storm does not erase science or remove every machine. It creates a severe test of resilience. Some regions would recover quickly. Others could remain without reliable power far longer, especially where equipment is old, grids are isolated, or replacement capacity is limited. The global picture would be uneven, shaped by latitude, geology, infrastructure, preparation, and the storm's magnetic character. Modern civilization is exposed because it has achieved extraordinary efficiency by linking everything together. The same connections that deliver food, energy, information, and medicine also carry disruption across sectors. A solar storm reveals those hidden dependencies. Electricity supports water. Water supports health. Fuel supports repair. Communication supports coordination. Navigation supports transport. Each system can endure strain, but none stands entirely alone. The sun does not need to destroy them directly. It only needs to push enough of them out of balance simultaneously, leaving civilization to discover whether its networks contain enough separation, redundancy, and patience to recover. The greatest uncertainty surrounding extreme solar storms is not whether the sun can produce them. History, spacecraft observations, and the physics of magnetic eruptions show that it can. The uncertainty lies in frequency, scale, timing, and consequence. A severe storm may pass through Earth's orbit when the planet is elsewhere. A direct impact may carry a magnetic field that couples weakly with the magnetosphere. Another event of similar speed and size may arrive with a prolonged southward field and transfer far more energy into near-Earth space. This same solar eruption can therefore produce very different outcomes depending on details hidden inside the cloud. This makes the risk difficult to express as a single number. It is tempting to ask how often a civilization-threatening storm occurs, but the answer depends on what qualifies as civilization-threatening, which measurements define the storm, and how vulnerable human systems are at the moment of impact. The sun provides the hazard. Civilization determines how much of that hazard becomes disaster. Estimates of extreme storm frequency often begin with a short instrumental record. Continuous satellite monitoring covers only a small fraction of the sun's life, while reliable electrical measurements span little more than the technological age. Events as large as the Carrington disturbance are rare enough that the sample remains small. One or two examples cannot define a precise cycle. Researchers therefore combine historical reports, modern spacecraft data, magnetic records, observations of other stars, and traces preserved in natural materials. Each source adds information, but each also carries uncertainty. Old accounts describe auroras and telegraph failures, yet they do not provide the global measurements available today. Modern instruments are precise, but they have not operated long enough to capture the full range of rare solar behavior. Natural archives reach farther into the past, though they often record energetic particles more clearly than the complete magnetic structure of a coronal mass ejection. A storm can be dangerous to satellites without being equally dangerous to power grids. And a strong geomagnetic event can occur without leaving a simple signature in every archive. For this reason, estimates vary. Some studies suggest that a Carrington-scale event has a meaningful chance of occurring within a human lifetime. One widely repeated estimate places the probability near 12% within a decade. though that figure depends on limited observations and assumptions about how extreme events are distributed. It should not be treated as a countdown or a fixed law. A probability does not reveal the year, and it does not guarantee that the next large eruption will strike Earth directly. It only expresses that the risk is not negligible. Over longest periods, the chance of encountering a severe storm rises, but the calculation remains sensitive to the data and model used. The danger may be lower than the most alarming forecasts, or it may be underestimated because the modern record has not captured the largest possible event. The phrase solar superstorm also creates ambiguity. It can refer to a storm comparable to the Carrington Event, an eruption larger than anything directly measured near Earth, or an event linked to the more energetic superflares observed on other stars. These categories should not be merged carelessly. The Sun is relatively calm compared with many young and magnetically active stars, yet observations suggest that stars with broadly solar characteristics can sometimes produce eruptions far larger than ordinary solar flares. Research published in the late 2010s raises the possibility that even calm stars may generate rare superflares over intervals of thousands of years. Such findings widen the upper boundary of what may be physically possible, but they do not prove that the modern Sun will produce an identical event on a predictable schedule. Stellar observations reveal possibility, not certainty. A flare seen on a distant star also does not reveal whether it launches a coronal mass ejection toward a planet, how the magnetic field is oriented, or whether that planet possesses a protective atmosphere and magnetosphere. The consequences on Earth are equally difficult to calculate. Some projections focus on temporary power loss, satellite disruption, radio blackouts, and economic damage. Others consider widespread transformer damage, prolonged regional outages, and cascading failures across supply chains. The difference often comes from assumptions about grid resilience. A model may treat transformers as vulnerable to permanent damage, while another assumes that operators disconnect them before heating becomes severe. One scenario may include coordinated recovery, spare equipment, and unaffected regions able to provide support. Another may assume simultaneous failures across several countries and delays in manufacturing replacements. The same storm can produce a manageable emergency in a prepared system and a prolonged crisis in an unprepared one. Geography adds another layer. High-latitude grids may experience stronger geomagnetic disturbances, but local geology can increase or reduce induced currents. Coastal regions may face different electric fields from inland areas. Networks with long transmission lines may gather more voltage than compact systems. Equipment age, transformer design, load conditions, and operator training all matter. A global solar storm therefore does not create a uniform global blackout. It creates a map of unequal stress. Some areas may see auroras and minor voltage fluctuations. Others may experience satellite problems, radio loss, or temporary grid shutdowns. A smaller number may face damaged equipment and slow restoration. The phrase global event describes the reach of the disturbance, not identical consequences everywhere. Unequal impact can complicate response because regions recovering quickly may become sources of aid, while heavily affected areas depend on transport and communication links that are also disrupted. The timing of the storm also matters. A grid under heavy demand has less operating margin than one carrying a light load. A storm arriving during extreme heat or cold places greater pressure on heating, cooling, and public health. A region already affected by wildfire, flood, conflict, or fuel shortage has fewer resources for a space weather emergency. Satellites may be more vulnerable during particular operations, and crews beyond low Earth orbit face greater risk if an energetic particle storm begins while they are outside protected areas. This is why civilizational risk cannot be reduced to the energy of the eruption alone. It emerges from the meeting between a rare hazard and a particular moment in human systems. The strongest claims often imagine complete collapse. Yet that conclusion requires several failures to align. A powerful coronal mass ejection must strike Earth directly. Its magnetic field must remain strongly oriented for efficient coupling. Geomagnetic changes must induce large currents in vulnerable networks. Protective actions must fail or arrive too late. Enough major transformers or control systems must be damaged to prevent rapid restoration. Communication, fuel, water, healthcare, and supply chains must then deteriorate faster than authorities in neighboring regions can stabilize them. Each step is plausible, but the entire chain is less certain than any single part. Yet dismissing the danger because total collapse is uncertain would be equally mistaken. Severe disruption does not need to end civilization to cause enormous harm. Days without power across a major region can endanger lives. Weeks can strain food, water, medicine, finance, and public order. Permanent damage to a limited number of critical components can slow recovery far beyond the duration of the storm itself. The meaningful question is not whether solar activity can return humanity to a distant age in one instant. It is how much disruption modern societies are willing to tolerate before strengthening the systems that prevent a rare event from becoming a long emergency. Uncertainty is sometimes used as a reason to delay preparation, but in risk management it often supports the opposite response. When the hazard is poorly timed but physically credible, resilience becomes more valuable. Better monitoring improves warning. Better models narrow estimates of arrival and magnetic structure. Stronger grid procedures reduce induced currents and prevent transformer saturation. Spare equipment, coordinated plans, and protected communication make recovery faster even when forecasts are imperfect. These measures also help during ordinary disasters. Preparation does not require certainty that the worst case will happen. It requires recognition that the consequences could be serious and that many of them are preventable. The sun offers no schedule and no promise of restraint. It may remain quiet through generations, or it may release a major eruption during a period of growing dependence on electricity and space-based systems. Between those possibilities lies a wide range of outcomes, from harmless near misses to brief disruption, regional crisis, or something larger. Science can define the mechanisms, identify warning signs, and estimate probabilities, but it cannot remove chance from the path of a coronal mass ejection. The uncertainty remains, not as a blank space where any fear becomes reasonable, but as a boundary around what is known. Within that boundary, one conclusion is steady. Extreme solar storms are rare, their effects are uneven, and their worst consequences depend as much on human preparation as on the violence of the sun. Preparation begins with an uncomfortable advantage. A severe solar storm cannot be prevented, redirected, or weakened after it leaves the sun, but much of the damage it might cause can still be reduced. Solar observatories can detect active regions, flares, and coronal mass ejections. Spacecraft between the Sun and Earth can measure the solar wind before it reaches the magnetosphere. Grid operators can reduce loads, alter network configurations, and protect vulnerable transformers. Satellite controllers can postpone risky operations and place spacecraft into safer modes. Airlines can adjust polar routes. Communication networks can prepare for disruption, and emergency agencies can coordinate before the strongest effects arrive. Together, these steps turn an invisible natural hazard into a managed technical problem. The first layer of preparation is observation. Telescopes on Earth and in space watch the sun across visible ultraviolet, X-ray, and radio wavelengths. Magnetograms reveal the structure of active regions, while coronagraphs block the bright solar disk and expose faint clouds expanding through the corona. When a flare begins, radiation monitors determine its strength almost immediately. When a coronal mass ejection follows, repeated images help estimate its speed, width, and direction. Models then trace the cloud through the solar wind, adjusting forecasts as new data arrive. A slow eruption may provide several days of warning. A fast one may leave less than a day. Even then, the arrival time remains uncertain because the cloud can accelerate, decelerate, expand, or interact with earlier solar material. Forecasting is therefore a sequence of narrowing estimates rather than a single exact prediction. The most difficult feature is the magnetic field carried inside the CME. Its orientation decides how efficiently energy enters Earth's magnetosphere, yet that orientation is hard to measure from far away. Scientists infer part of the structure from the source region, the shape of solar filaments, and the apparent rotation of the eruption. The final direct measurement comes from spacecraft positioned upstream of Earth, where the solar wind passes before reaching the planet. These monitors provide a last warning about speed, density, and magnetic direction. If the field turns strongly southward, the risk of a severe geomagnetic storm rises. The warning may be brief, but power networks and satellite operators can act more effectively when procedures are prepared in advance. A few minutes of certainty can be useful only when decisions have already been planned. Power grids require the most careful preparation because they connect the storm to essential services on the ground. Operators can monitor geomagnetically induced currents, transformer temperatures, reactive power demand, and unusual voltage behavior. During a strong warning, they can reduce transfers across long transmission lines, bring additional generation online near demand centers, and place vulnerable equipment in safer configurations. Some lines or transformers may be temporarily disconnected to prevent internal heating. This can cause controlled local outages, but a planned interruption is less dangerous than uncontrolled damage. Networks can also improve resilience before any storm occurs by installing better current sensors, upgrading protective relays, strengthening grounding, and using devices that limit unwanted direct current. Grid models that include local geology can identify regions where surface electric fields are likely to become strongest. Preparation becomes more precise when operators know not only that a storm is approaching, but which parts of the network are most exposed. Large transformers remain a central concern. Their protection requires more than emergency switching. Utilities can maintain strategic spares, standardize designs where practical, and develop transport plans for equipment too large to move easily. Governments and manufacturers can coordinate production capacity so that many regions are not competing for the same limited replacements after a widespread event. Mobile transformers and temporary substations can restore partial service while permanent units are installed. The same equipment and procedures can support recovery from floods, fires, earthquakes, sabotage, and ordinary mechanical failure. Satellites require a different form of readiness. Operators receive space weather alerts and can delay sensitive maneuvers, software updates, or instrument operations. Spacecraft may be placed into safe mode, reducing electrical activity and orienting vulnerable surfaces away from damaging conditions. Redundant computers can correct radiation-induced errors, while shielding and fault-tolerant components reduce the chance that one particle strike becomes a mission-ending failure. Orbital models can include increased atmospheric drag during geomagnetic heating, helping controllers maintain accurate tracking and prevent collisions. Constellations with many satellites require coordinated responses, because a storm can affect hundreds of spacecraft at once. Resilience depends not only on protecting individual machines, but also on preventing congestion, lost tracking, and simultaneous service failure across an entire orbital network. Human spaceflight raises the stakes. Astronauts beyond the strongest parts of Earth's magnetic protection need shelters with additional shielding, radiation monitors, and procedures that can be followed quickly after a particle warning. Mission plans can limit exposure during periods of high solar activity, though the solar cycle never removes risk completely. Lunar bases and spacecraft traveling toward Mars must treat solar radiation as an environmental hazard similar to vacuum or extreme temperature, water, food, fuel, and structural materials can be arranged to surround protected areas. Accurate warning cannot stop the particles, but it can move crews away from the most exposed parts of a habitat before the peak arrives. Communication and navigation systems also benefit from layered alternatives. Radio operators can shift frequencies, use different propagation paths, or rely on satellite and terrestrial links in combination. Aircraft can avoid polar routes when high-frequency radio and navigation become unreliable. Ships can carry independent navigation methods, while critical infrastructure can maintain local timing sources if satellite signals are disturbed. Emergency networks can reserve capacity for essential traffic and use hardened equipment with backup power. These measures do not preserve every service at full performance. They preserve enough function for coordination, safety, and recovery. A resilient society does not require every system to remain untouched. It requires failures to remain limited, visible, and reversible. Public planning matters because even a well-protected grid may experience deliberate shutdowns or temporary instability during a major storm. Hospitals, water plants, fuel terminals, and communication centers need tested backup systems with realistic fuel supplies. Local authorities need ways to share information when mobile networks are overloaded or offline. Supply chains for food, medicine, and replacement equipment need priority routes that do not depend entirely on one digital platform. The difference is that a solar storm may affect several distant regions at once, reducing the amount of outside help immediately available. Coordination across national borders therefore becomes important, especially for shared grids, satellites, aviation, and manufacturing. International warning systems can spread observations quickly, but warnings matter only when organizations trust them and know what threshold requires action. False alarms carry costs. Disconnecting equipment, rerouting flights, or placing satellites into safe mode disrupts normal operations. Forecasts must therefore communicate uncertainty clearly, describing not only what may happen, but how confident the estimate is. Operators can then choose actions proportional to the risk. Better science improves this balance. More spacecraft viewing the Sun from different angles can refine the direction of an eruption. Better measurements of the corona can improve estimates of magnetic structure. Stronger models can represent interactions between multiple CMEs and the changing solar wind. More ground sensors can map regional electrical responses during a storm. Each improvement reduces uncertainty, but none produces perfect foresight. Preparation must remain effective even when forecasts are incomplete. The most important defense is not a single satellite, transformer, or emergency plan. It is a culture of continuity in which rare hazards are taken seriously without being exaggerated. Solar storms do not require panic, and they do not justify the belief that modern civilization is helpless. The atmosphere and magnetosphere already remove the most direct danger to life at the surface. Engineering can address much of what remains. The challenge is that protection must be built during long periods when the sun appears quiet and the threat feels distant. Infrastructure budgets favor immediate needs, while rare events invite delay. Yet the cost of preparation is often far smaller than the cost of replacing damaged systems after a major storm. The final question is therefore not whether the sun will erupt again. It will. Nor is it whether every strong eruption will become a disaster. Most will not. The question is whether civilization uses the warning offered by history, science, and near misses to reduce the consequences before the next direct impact. The sun remains beyond control, but the shape of the outcome is not. A storm can arrive as an unavoidable event and still meet a prepared world, one able to dim parts of its electrical network, shelter its machines, protect its crews, and recover without allowing temporary darkness to become lasting collapse.